Hello everyone, this is the ENGG1300 Term 3 crash course for the students who are doing it with the MEC stream. I ran this crash course today at uni and I recorded it and then it turns out none of it actually recorded, which was really unfortunate, so it means I now have to do it all over again, but that's alright. I think literally everyone who's run a crash course before has had to do this because the recording just pretty much like works only like half the time. So today, this will probably end up being faster than the actual one because the actual one I took a break and I got people to scan the QR registration form, and you'd have to do that. So I'll probably honestly try and do this in an hour and a half because I got something to do. I got a tutor at 7, so I'd like to do this, but I won't rush. Don't worry. If it ends up taking longer, I'll just finish it off after my thing that I have later tonight. We'll wait and see, I guess, how long this takes, but it should be only an hour and a half, maybe 2, if I go really slow. So just want to give you guys a bit of context. So this is the Term 3 2023 final. You guys don't have this one. If you're watching in 2025, that is, you guys don't have this one. Callum hasn't provided it to you, but I'm providing it to you. It is in the description. Just check the description, it's there. With my answers as well, and I've gone through and checked my answers. There might be some small mistakes here and there, especially question 8. I can't really guarantee question 8 I've done properly, but the rest of it should be correct. I've double checked it with ChatGPT and Gemini and all that, just to be sure. I don't recommend using AI if you don't know the stuff, but if you know the stuff and you just want to confirm you're correct, it usually helps. It's usually a good way of like double checking that you've done it right. Just run it by AI and see if it does the same method and it gets the same number. In my case, it did. Okay, so this is the final from 2023. I still have a copy of it because it was actually online in 2023. It's not online this year for you guys, unfortunately. It would be great if it was, because it's open book, but then usually it was open book, but usually open book exams are harder, I do admit, and hopefully your one will be easier because it's closed book. Anyways, let's do it. Let's do this. Okay, I'm going to power through. We're going to start with question 1, which is free body diagrams in equilibrium. So for the loaded structural member below, first we're going to replace the given force system by a resultant force and a couple moment at point B. So we just really need to decompose this. This is like bare bones, simple, straightforward ENGG1300. Like this is the classic stuff, but it's also what you guys would have done, like literally in week 1. So it's been a while since you've done it. So good to go. Good to do a bit of revision. Okay. So I'm going to trace it here. And then I'm going to move it to the next page. Obviously, you can't really do that if it's a written exam, but since I'm doing it on an iPad, and I actually did it on this very iPad in 2023, almost exactly 2 years ago. So I can do this type of thing, just trace on it. So the moment is 15 kilonewton meters. Now remember the moment sign convention, which is that anti-clockwise is positive, okay? So we're going to say that's positive. You can do whatever you want. You can technically say anti-clockwise is negative, but that's just going to confuse you because pretty much, no one would really say that, so you'll be the only one doing that. Technically you can do it, but you'd be the only one. Okay. I'm also going to add A, Y, and AX. We don't need it for part A, but we are going to need it for part B, and that'll become clear soon why. Okay, so that is our member. We also have F1. F1 is striking at a degree of 30. And it is 4 kilonewtons. So remember, you can follow along. I've got the paper attached below, so you can actually follow along if you'd like. I would recommend it. Like follow along with my working. And then this is 1. So this is another different one. It's 1 kilonewton per meter. Okay, that's 10 degrees. And then this is 30 degrees. Okay, and that is it. I'm going to now move this to the next page. Just lift it up. Okay, so just before I move it, what we're trying to do is figure out the moment and force at B that'll kind of counteract everything else, okay, and ensure this is an equilibrium. No, ignore what I just said. We're trying to find the force and moment at B that is equal to everything else. That's what I meant to say. So that if I applied a force and a moment at B, then it would be the exact same as these three forces. And in effect, I wouldn't even need to apply those three because I'd just be applying it at B. What's the equivalent is what we're trying to ask. Another thing really quickly before I keep going, this paper, and I explained this in the crash course today, it's really weird to have to go over it again. It's like deja vu, but that's okay. You gotta double check that recording software is working, I guess, and I didn't do that until the very end. Anyway, there were these reflective questions that Kellerman asked us. So you guys would have had reflection questions, I'm pretty sure, this term, but the difference is I don't think Kellerman can examine you on it. Whereas he was able to examine us on it through some weird, complicated tech wizardry where he'd actually give us our picture, the picture we took, and then he would, sorry, let me turn off low power mode. Yeah, he would give us the picture we took and then give us a question on it or something. Anyway, so let's do this question. All right, so this is A, I think A is here. C is here, and then B is here. All right, and we should add some distances too. Okay, so this is always, and I said this constantly today, is you absolutely need to have good free body diagrams. It's an absolute necessity in ENGG1300, and honestly beyond. Okay, it's always a necessity. Always be thinking about that. Okay, so replace the given force system by a resultant force and couple moment at B. So we need to kind of decompose everything into horizontal and vertical components. Okay, so we know that Fx, the sum of Fx is going to be equal to the x force at B. Okay, so I guess we can call it x, sorry, Bx. We'll call it Bx, okay? That's kind of what we're looking for. Okay, so what we end up with, okay, let's decompose these. All right, so we have a force of 4 hitting at 30 degrees. But we want to decompose it into just the x components. So let's go back to high school trig. That will be for sine 30. Okay, and then also this one. Okay, remember vector addition. If a vector starts and ends there, then any number of vectors that starts and ends at the same spot will be the equal. Okay, so this vector is the same as this vector technically because they start and end. Okay, so that's like 6 vectors. It's still the same, like those vectors are equivalent because the vectors start and end at the same spot. That's how vector addition works. Okay, plus 1 cos 10 degrees. All right, and if you do that, you get 2.98 kilonewtons, okay? And that's Fx. Now for Fy, same thing. This time, it's, okay, we're going to ignore Cy, Ax, Ay. That's for part B. Don't worry about those yet. So this time it's that one and that one, okay? So the 4 one first, so that's going to be By, and that equals 4 cos 30. Oh, but it'll be negative, sorry, because it's going down. So always remember your conventions. X is positive right, negative left. Y is positive up, negative down. 4 cos 30 plus 1 sine 10. Okay, and you should get minus 3.29 kilonewtons. Okay? So, it's asking us for the resultant. Okay, it specifically asked for the resultant force at B, which basically means we need to actually find the magnitude, the square root of both. Okay, so 2.98 squared plus 3.29 squared, and you should get 4.44 kilonewtons. Okay, and that is the resultant force, but we still need the angle. Okay, so we know. So let's just honestly and this is what I did in the exam as well. I should clarify that this. I think I already said, didn't I? This is the actual exam I did in 2023. So I was looking back over my answers, and what I did was I drew it. So, and this is what anyone should be doing. So it's obviously to the right by 2.98 and down by 3.29. Okay, so it's going to be something like that. All right, and we want to know what angle it's making with the horizontal. I don't actually know if it's specifically asked for the angle, but I'm pretty sure the implication is you need the angle, okay? There's no point in having a resultant force unless you have an angle, okay? Yeah, so, and that's alternate angles, obviously. So we're trying to look for this angle, and that would give us this angle. Okay, so if I was to draw it onto the diagram here, it'd be that angle. Beautiful. Okay, so, yeah, so literally just tan theta equals 3.29 over 2.98. And that, I did it. I'm just going to check. I don't actually even need my calculator because I already did all of it before. So I did this all last night. I did the paper. I did the paper 2 years ago, and then I just went back over it last night to check my answers were correct. And a lot of them weren't, actually. A lot of answers weren't, but that is not because I'm bad at ENGG1300. It's just because I did it all in 2 hours in the exam, and obviously I was rushing. So I made a lot of silly mistakes, but I went back through yesterday and corrected it, so all my answers now should be correct. But it was very interesting. You don't usually get the chance to go back over a final. If you ever get that chance, you'll spot a lot of silly mistakes. I made quite a lot of just very small mistakes. I'm going to actually point them out while we go through this crash course so that maybe you can avoid making them on the day. So anyway, so that's the angle there. 47.8 degrees. So we now know the resultant force is 4.44 kilonewtons at an angle of 47.8 degrees. Okay? But we still need the resultant moment. Okay? There's still going to be a resultant moment. Okay? So let's hope you all remember moments. The most important rule of a moment is if the axis of the component passes through the point that we're calculating moments around, then that cancels out. Okay? So, for example, at this point, that doesn't pass through B. The vertical component of the 4 doesn't pass through B. This is the horizontal component. Okay, of course, the horizontal component's not actually up there. The horizontal component's going through the point. And what other point is it going through? It's going through B. So we can ignore the horizontal component of F1. That's the F1 force, I'm pretty sure. And we're going to do that. So summation of moments at B equals 0. Okay, we're going to say anti-clockwise is positive. That's standard. You got to do that. Okay, so moments at B. So we've got the 4 cos 30. That is inducing a clockwise motion. So we're going to say that's negative. And remember the lever arm. It's a very important thing. Remember a moment. So with force calculations, with X, with Y, you don't include the distance. But with moments, you need to include the distance between the force and the point. Okay, because it's torque, right? Like if you think about a door handle, the door handle right behind me. Oh, I might have cropped that out in the edit. Actually, never mind. Yeah, if you do that, the door handle needs to be further from the point, right? If it's actually at the hinge, you're never going to be able to open the door. It's the same reason why if the force passes through the axis, through the point, you would never induce a moment. Okay, so minus 4 cos 30 times 1.5, and then we're going to have this one as well. The vertical component of F2 is not going to be applied, but the horizontal component will, because it doesn't pass through B. And that will be inducing an anti-clockwise motion as well. So that would be 1 cos 10 times 2. They're both cos, is that correct? Yeah, they are both cos. And then plus 15, because there's a 15, the induced moment. Never forget induced moment. It's very easy to just kind of blank on that. That should equal 0. Oh, not 0, sorry. MB. My bad. That should... Okay, so we're not doing any... This is not equilibrium yet. This is just finding reactions. Okay, so that's going to equal 11.77 kilonewton meters clockwise. Okay, so you'd get a negative number. Yeah, really, you'd get a negative number from that? Okay, according to my answers you would. Let me just double check, get my calculator, 1 moment. Sorry, it is counterclockwise. It's positive, it's counterclockwise. And I actually wrote counterclockwise and I just misread my answers somehow. Okay, and yeah, that's it. So, the resultant force is 4.4 kilonewtons and 47.8 at 47.8 degrees. And then the moment, the induced moment is 11.7 kilonewton 0.77 kilonewton meters. Okay, up. And that is the answer to part A. Now for question for part B. So part B is determine the magnitude and direction of the points of the reactions at points A and C. Okay. So we'll go over this really quickly. I'll just do it on the same page actually. So we need to find CY, AY, and AX. So something you need to get used to in ENGG1300 is knowing the fastest way to solve a problem by just like getting rid of as many unknowns as you can. So what reaction, looking at this diagram, should I do moments at B? Should I do moments at C? Should I do moments at A? Should I even not do moments at all? Should I try and resolve the X forces or the Y forces? There's actually a lot of options here. And you could technically start by trying to find AX. And why is that? I'll tell you why. AX is the only unknown X force. So you could do that. It's the only unknown X force, but I'm going to do something different because CY is the only unknown that would interact if I just chose moments at A, and that's what we're going to do. If I choose moments at A, AY and AX both evaporate because they aren't going to induce a moment at A. That's impossible. As I told you, the door handle at the hinge is never going to open the door. The reactions at A are never going to induce a moment at A. So that's what we're going to do. So if you look at this diagram, CY is happening at a distance of 4 from A, or from the axis of A, okay? So CY, and it's clockwise, so it's a negative, minus CY times 4. Then we have this one, so the force here, the 4, so the 4 sine 30 is happening, and that's also clockwise, so minus 4 sine 30 times, so that one's going to actually be times 3 this time, and we also have this one, okay, so this force pointing down, that's at a distance of 1.5, okay, so that's a negative, yeah, that's a negative as well, so it's a lot of negatives. Minus 4 cos 30 times 1.5. Okay, and we have one final one. Okay, it's not the up. So at F2, this is F2, the up force passes through A. So it's not going to be that, but the horizontal one doesn't. So it's going to be the horizontal one, and it's going to be negative as well. There's a lot of negatives here. It's also clockwise. Minus 1 cos 10 times 1, that equals 0. Okay, and if I was to solve that, you end up with CY equals 0.70 kilonewtons down. Okay, now check this with SkySieve, and that should be correct, assuming SkySieve is correct, which it is. Okay. So now the summation of y is 0. This one's easier, okay, because you already have CY, and you have this, and you have this, so you just add it all up. So we're looking for AY now. So AY minus 0.70 kilonewtons, minus 4 cos 30, plus 1 sine 10. That should be 0. Okay, and then what do we get? We get AY equals 4 kilonewtons up. Okay. Why am I writing down and up instead of just the sign? It just helps. I mean, you can write the negative and positive. You probably should while you're doing the working. But for the final answer, it's kind of actually clearer to just write that. Okay, so that's question 1 done. Alright, I decided not to commit the same mistake twice. I just was double checking that the recording's working this time, and it is. I'm recording it a different way, so I'm going to just record it separately on my iPad. I don't trust OBS anymore. Don't use OBS. For iPads, it's actually pretty good for everything else, not for iPad recordings, I guess. Okay, so now we're going to do another very classic ENGG1300 question, which is structures and trusses. We're going to go over method of sections and method of joints. Now this question takes a while, so I'm not going to go through the whole question, but instead I'm going to each question requires you to find the force in a member. So I'm just going to find one for each method, basically. So, I'm going to screenshot this. take it to the next page. Okay, it did not paste. There we go, it did paste. Okay, so that is our truss. So we're being asked in this question to resolve this truss in essence. And we've been given a bit of information. We've been given that F1 is 12 and F2 is 20. All right, look at us go. So how are we going to do this? All right, well, it's a method of sections question. We've been asked to find the forces in BC, that's BC, BE, that's BE, and FE. We're not going to find all of them, but pretend we are. Okay, now straight away you can see that these forces all act on the DEC, the DCE, whatever you want to call it, truss. Okay, so what we're going to do is we're going to do method of sections with just that truss, because we're going to make a cut there and then treat it all as external forces. But before we do that, we need to resolve the external forces before we get to internal, the actual method of sections. Okay, and we need to do that because this truss has a force at D. Okay, so we have AY, AX. Okay, and there's an AX because that's a pin. DY is just DY because there's no pin. It's a rocker. Yeah, that's it. Okay, so moments at A equal 0. So yeah, let's just summate it. Okay, so dy is obviously causing an anti-clockwise motion, so dy times 6, okay, because it's going anti-clockwise. F1 would be clockwise, so that would be minus 12 times its distance from A, which is 3. F2 is going, it would be clockwise, as you can see, it would be clockwise like that, so it would be negative, and it would be times 2, and that is 0. Okay, so if you were to simplify that, you should get dy is 12.67 kilonewtons. I did check that on SkySieve. So we don't need A for this, not for part A, and we actually don't for part B either, but the more important thing right now is we don't need it for part A. Okay, and that's good. So we're going to ignore AY for now. And the reason we don't is we're now just going to literally just look at that, okay? Okay, so this is 12.67 kilonewtons. Okay, so we have BC. We have, sorry, we're going to call FBC. We also have FBE and FFE. Okay. All right. Yeah. And we're going to decompose everything just as usual. What is the angle of FBC? I'm sure you're wondering. Just have some water. What is the angle that BC is making here? Well, just do some trigonometry. We know that this is, so it's this triangle. So this is, that whole thing is 3, and this part is 2. So you know that this is 1, and then you know that that's 2. Okay, so 1, 2, tan inverse of 1 over 2, you end up with 26.6 degrees. Okay, and I think we now have enough information to find FBC. Okay, and that might surprise you. It doesn't look like there's much information yet, but, and this is now kind of going back to what we just did in question 1. There is an equation here that we can come up with that just eliminates everything but one unknown, and that is moments at E. Okay, if you find a moment at E, you eliminate, bang, that's down, bang, that's down. Okay, now you just have 12.67 times 2. And remember that that is anti-clockwise, so that's positive. Whereas this, the FBC is negative, because it'd be clockwise. Okay, so minus FBC cos 26.6 degrees. Okay? And now this is the important thing you need to do, is you need to times that by 2. Why are we timesing it by 2? Because it's the lever arm, okay? And then you might be tempted to add this, the downwards one as well, but again, the downwards of FBC would pass through E. So that doesn't do anything, okay? Because it's negative. It passes through E, so it's not going to have an effect. It's not going to induce a moment, okay? So, if you solve that, you end up with the force of BC is 14.2 kilonewtons. It's positive, so it's in compression. So as a quick revision, hopefully you remember this, if it's pointing into the joint, we're going to say it's in compression. That's just convention. If it's pointing out of the joint, that is tension. I assumed for all of these that they were all in compression. That's obviously pretty unlikely. I, in fact, think it would probably be impossible. But just assume, and then if you get a negative, then you know it's in tension. Because just by looking at this, you don't really know what's in tension or compression, unless you're like a magician. So just assume they're all in compression, and then if it's negative, you know it's in tension. Yeah, that's the answer. So that is method of sections. Method of joints is next, okay? So I'm just going to literally, for this part, copy my diagram from here. So to save us a bit of time from drawing it. So this is the joint at B. Okay, so if you were to scroll back up on your sheet, and you see that this is the FBD at B. Okay, we have a 12 kilonewton force being applied at B. We also have the AB member, the BF member, and then these two members as well. 7.61, what is that applying to? That is FBE, okay? We didn't find FBE in part A, but if you were to go on and find it, that's what you should get. And then this is FBC, and we did find FBC. Okay, you can see it again. I would assume they're all in compression. That's obviously ridiculous. They're not all going to be in compression. But you can assume whatever you want. Doesn't really matter. Now, I'm going to find X forces first. Why X? Well, obviously you can't do moments because there's one joint here. There's only 1 point. How can you do moments when there's only 1 point? That doesn't even make sense. You could do Y, but the problem here is we have two unknowns. Okay, we have AB and BF are both unknown. We want to find one of them, and if we try and do Y, they're both involved in Y. Okay, AB has a vertical component, and BF only has a vertical component. It doesn't have an X component. Aha, there you go. BF doesn't have an X component. That's what makes X the best thing to find, because if we try and find FX, we're only going to have AB as the unknown. Okay. And I found all these angles from trig. I think you can, you guys all did year 10 high school. So FAB cos 56 minus 7.61 sine 33.7. And the reason it's minus, this one's pointing right, okay, so up and right. But then this one's pointing left, okay, it's up and then left. So that's why that's negative. Same with the 14.2. And then we have the plus 12 equals 0. So you should get, pretend you simplified all that. I'm going to skip a few steps there. You should get FAB equals 8.8 kilonewtons in compression. So surprisingly enough, AB is in compression. However, I will spoil the answer for you. If you were to do BF, you end up with BF is in tension. Okay, so you'd be thinking like, why on earth are there so many members in compression here? Well, it's because BF's in tension, okay? And that kind of counteracts everything. So we've now done questions 1 and 2, progressing pretty well. Hopefully that's all making sense so far. Those are the two more straightforward topics, but don't kid yourself. Like, they're still difficult in their own way. They still take you ages to master, so spend the time on them and don't be disheartened. Okay. Now we're getting to frames of machines, which is now, this is like getting a little bit more annoying. I actually skipped this question today in the workshop. And I think I will skip it again because it is like really quite similar to the first two. And I want to focus a bit more on dynamics. I've put the answer in my description and I double checked the answer using like ChatGPT and all that and Gemini, it should be right. I can't 100% guarantee. I'm pretty confident it's right. I only say that because I don't want to like. I want you guys to also check yourselves and not be concerned if you get a different answer. I'm pretty sure it's right. If you're getting the same answer as me, that means it's definitely right. So we'll leave 3 for now. Maybe at the end I'll get back to it, depending on what time it is. It's like 6:11 right now. Oh yeah, right, I'm sharing my screen, so you can see exactly the time I'm recording this. Let's do section 4. Yeah, at 7 o'clock I have to tutor someone. So, I still tutor. High school maths. Alright, so. Shear force and bending moment. For the loaded beam shown. Okay, so this is like really classic engineering, civil engineering, quite frankly. Very, very important stuff. You need to know this. I think out of every topic in this test, this is probably genuinely the most important, like in terms of civil. So draw the FBD of the beam. I actually did draw the FBD in the session today. I think it's a bit of a waste of time. I think you guys should know how to draw an FBD by now. At the very least, you can look at how I draw it. Okay, so this is it. This is the FBD. Okay, I'll revise how I found the R equals 20, but I won't show you how to do the FBD. I feel like that's pretty simple. Okay, so that is that. All right, so how did we find the 20? Well, first of all, you're probably wondering, why do we even need to do that? Well, you need to do that in order to find AY and BY, which is part of the question. It asks us, find the vertical reaction A and then the vertical reaction B, okay? So, W, the 20 kilonewtons per meter, is what we call a distributed load. Okay, it's happening over a certain length, in this case 2 meters, right? But it's a triangle, which is a bit annoying. So basically, the first we want to find the force amount. How much force is that triangle actually exerting on the beam? It's literally just half base height. Okay, the base is 2 meters, the height is 20 kilonewtons per meter, and then you just times it by half. So 20 times 2 times half is 20. So you actually end up just back with 20, but that's more by coincidence than anything. That is the resultant. That is the amount of force in total that triangle is exerting on the beam. Now, how far is it from, like, what position is it on the beam? Is at 2/3 from the base, from the tallest side. And how do we find that? The resultant of a triangle load is always 1/3 of the base length from the longest side. Okay, and 1/3 of the base length here is 2/3. Oh, so that's why we end up with 2/3. Okay. And yeah, that is how you do that. I think you guys should be able to find these on your own. I would love to spend time on it, but it's like really we've already done that today. I'll tell you really quickly. Just find the moment at write an equation for the moment at A. Okay, and then this is clockwise, so 10. This is anti-clockwise. This is anti-clockwise as well. So it'll be plus 7.78 times 3. And remember, you don't times this by anything. You don't times an induced moment. An induced moment is just an induced moment. You don't need to multiply by lever arm. And then the 20 is just, that'd be negative because it's clockwise. Minus 20 times 5/3. Okay, so now we're up to the kind of the harder part, I'd say, which is drawing a shear force and bending moment diagram. How are we going to do that? Okay, well, this is how I do it, all right? And this is how I recommend you do it as well, which is, let's draw the reactions first. So we know that it goes up by 12.22 at A. Okay, so that is 12.22. Okay. Now, what we also know is that a beam has to end up at 0. Okay? It needs to end up at 0 because it's in equilibrium. So it can't be lingering. Like, we can't have a value up here at the end or down here at the end or something. It needs to be 0 at the end. So it needs to be here, literally. How are we going to get that? Well, first of all, we know that whole thing needs to be 0. And how have I come to that conclusion? Well, if it needs to be 0 at the end, it also has to be 0 at B. Again, the reason it has to be 0 at B is nothing's happening here. between B and the end of the beam, nothing happens. So there's no opportunity for it to come back to 0 any other way. Okay? So we know that. But we also know that BY is up by 7.78 and it ends up at 0. That means that this is minus 7.78 right there, okay? Because it goes up by 7.78, okay? And that is how you do that, okay? One last thing, nothing happens between AY and here, so we know it's linear for that whole time. Okay, so now it's a question of how do we close the gap? Like how do we, join up these two graphs? Is it going to be like that? No, it's not going to be like that. Is it going to be like this? Well, yes, and I'll tell you why that's the answer. The reason that that's the answer is, well, first of all, this is a linear load. It's a linear distributed load, okay? So the shear force diagram will just be the integral of the load, and the integral of the load in this case is going to be a parabola, because the load is a line, a linear line, and so the integration will be a parabola. Sorry, my dog's barking, as you can probably hear. Or maybe you can't. I don't know how good the noise cancellation is on this. The reason it's concave up and not concave down, I think you guys should know. You guys are smart, but if you don't, it's because this is getting closer to 0. Okay, and then at that point it's 0. That means that the gradient is going from like 20 to 0. Or it's really negative because it's a negative load. Technically it's negative 20. Okay. But yeah, it's negative. And so that's why it's getting from really negative, which is this part, is like really negative, to like completely positive. Sorry, to 0. It's to 0. Okay. So that is how you draw the shear force diagram. And obviously you probably need to put a bit of labeling on it. I didn't do any labeling. That's 0, that's 1, 3, 5, and that's A. Shear force diagram done. Bending moment diagram. Okay, well, we know that there is a 10 kilonewton meter force anti-clockwise. So as far as I know, you got to do that. Okay, so that's going to be there. So we know it's going to go down from 10 to 0 because again, it just needs to. Sorry. Yeah, and as far as I remember, do double check this. As far as I remember, the convention for these graphs is if it's counterclockwise, the graph will go. Counterclockwise is actually negative on the graph, assuming that you're putting positive on the top axis. Okay, yeah. So, because this is inducing what is, yeah. Honestly, yeah. We'll just keep going. Remember that the integral of any graph is just the area. Okay, in this case, the area of this is 12.22. So we know it's going to go from 0 to 12.22. All right, cool. Okay, yeah. So it's going to go from 0 to 12.22, and then what is it going to do? Well, we also know at this point, if it's at 10, it needs to stay at 10. Because again, nothing happens between B and the end of the beam. So we know it needs to stay at that. And that's B, that's 3. That's B. So what is it going to do from here to here? Well, it's positive first, and then it's negative. That means that the graph keeps increasing, and then it starts decreasing again. Okay, so it would be something like that. Okay. And this is where the maximum bending moment would be. We don't know at what point that is. We can only guess. Looking at the graph, it seems to be around about a bit below 2. I know the answer to the next part. It is indeed a bit below 2. Yeah, so that's how you draw the diagrams. That's how you draw the graphs. Now, part C was honestly really hard. I spent a while on it yesterday, like redoing it. I got it wrong in the actual test, but then I redid it yesterday. I'm going to show you my method. I feel like it's a bit complicated. I might even just talk you through it instead because it took me a while. And I think honestly I'll just talk you through it. So here it is. This is the solution I came up with. Okay, I'm going to just talk you through it. So the question, as a refresher, is find the maximum bending moment of the graph. Okay, of the beam, and at what point on the line it is. Okay, and I did double check this with SkySiv. I've said that. I know I've said that a lot this test. I just want to reassure you guys. So we need to first find the equation of the load. That's what it should say. It should say load, not graph. So I don't know why it's so thin, but anyway, we need to find the equation of the load being applied. Okay, and so what I did, I just like literally just used some classic coordinate geometry. What is the gradient of the load? Well, if we say that this, we could just literally say that that point is, it's occurring at x is 3 because it's 3 meters along the beam, and then the load is 0 at that point. This is occurring at x is 1 across the beam, and then the load is minus 20. Okay, so then I found the gradient of that. Okay, and the gradient you end up with minus 20 minus 0 over 1 minus 3, you end up with 10. That is the gradient. W minus 0. Okay, so we're trying to link W to X. Okay, so W, this equation is literally just the Y minus Y1 equals MX minus X1. I'm just using that. So I really, for this question, I went back to first principles. Okay, I literally just was like, what is the most basic way to do it? And we literally just need to find the equation. That's the only way you can find the maximum, is to find the equation. I mean, there are other ways, but you know, that's what I'm going to do. Okay, you end up with this. The equation of that triangle is 10x minus 30. Okay, and maybe some smart people, you'd be able to deduce that just by looking at it, but I needed to actually do it like fully. So the shear force is the integral of 10x minus 30, and that ends up being 5x squared minus 30x plus c. Okay, so now we have our equation for shear force. Okay, but when x is 1, v is 12.22. Okay, we know that looking at our diagram because it actually starts at 12.22. This is what we're trying to find the equation of. Okay, it starts at 12.22 at x equals 1. Could have easily just as easily said when x equals minus 7 equals 3, shear equals minus 7.78. Okay, anyway, that ends up with c equals 37.22 if you do that. So now we have our equation for shear. Okay, we know that the maximum moment is going to be whenever v is 0. So x is either 1.75. Okay, so you do the quadratic formula. So quadratic formula, plug that into the quadratic formula, and you end up with x is 1.75, or you would get x is like 4.74 or something. But remember, because quadratic formula is always going to be 2 answers. Remember, you want to take the negative because the domain is 1. Sorry, not the. Yeah, you take the negative because the domain is 1 is less than or equal to x is less than or equal to 3. So it's not going to be 4.74 because that's outside the domain. So we now have the location, and you do a sense check, look at the graph. Does it make sense that this maximum is at 1.75? Well, I think that is about 2 and that is about 1, and that does seem, it actually looks like it's a bit more like 1.5, but you know, this isn't the most scientifically accurate diagram. 1.75 makes sense, so that feels like we're on the right track. Okay, now for the moment. The moment is the integral of the shear, which is 5 over 3x cubed minus 15x squared plus 37.22x plus the constant. So when x equals 3, the moment is 10. So 10 is equal to 5 over 3 times 3 cubed minus 15 times 3 squared plus 37.22 times 33 plus c. Okay? We're trying to find the constant. All right? And to be clear, I just got that from the graph. You know, scroll back up. So you end up with the constant is minus 11.66. So the moment equation ends up being this. Just plug in x equals 1.75, and you end up with the maximum moment is 16.46 kilonewton meters. So that is the maximum moment at 1.75 meters. My gut is telling me this is the only way to do this question, but the mark, it's only 1 mark for all of that. Okay, Kellerman's only giving you 1 mark out of 5 for this. So because it's only 1 mark, it's entirely possible that there is a faster way to do this, but this is definitely the most rigorous. Just find the equations of the shear force and bending moment diagrams, and then just, you know, solve, I guess. yeah, so that is the statics part done. This is where I gave everyone a break in the workshop. I'm going to give myself a quick, like literally 1 minute break and just check that the recording's working. And then we're going to move on to dynamics. Alright, welcome back. So we are now going to continue. I'm now standing up. I have a standing desk, which is really nice. It's good to... God knows we engineers sit down too much unless you're a site engineer, which you may not be. I'm not going to lie. I feel like a lot of engineers just end up sitting in office jobs. So part 5 is basically the first part of dynamics. The good news if you hate dynamics is so do I, and it's not really a civil topic. It's a mechanical topic that you just kind of have to learn because it's just whatever, like, you know, like money to the uni, I guess. I don't know. Okay, to be fair, there's probably a legit reason we have to learn dynamics. But I certainly don't use it as much as a third year student as I use statics. I guess for context, in doing and preparing for this crash course, the static stuff was really straightforward for me. Like, I could do all that. This dynamic stuff required a lot more revision. And you may even notice that I might be a bit slower with this stuff, and I do apologize for that. I've double checked the answers and they should all be correct, but I might be slower because it's I would say I'm a decent bit rustier. I think the static stuff is like my forte, like any civil engineer, and the dynamics is where it gets a bit harder. Okay, so the car has a forward speed of v and a forward acceleration of a. An observer B is riding in a chair on the Ferris wheel. You may assume B is a point on the Ferris wheel that is fixed to the wheel. The Ferris wheel has an angular velocity of omega and radius of r. Determine the magnitude of the velocity of the car relative to A relative to B. I will get to part B later. Let's just do part A first. In terms of relative, this is just like literally just remember the equation. I know your exam is closed book for some reason. I assume Kelman's going to give you like a formula sheet though. So, the velocity of A relative to B is just the velocity of A minus the velocity of B. So, what's our goal here? What are we trying to achieve? Well, we literally just want to find the velocity of A. Oh, hang on. Wait, they've already given us the velocity, haven't they? Sorry. I was trying to sound sarcastic. Let's just start, okay? So, we're going to like draw a free body diagram first. So, okay, yeah, 1 moment, I'm getting a message. Getting distracted, guys. This is why you turn off your phones when you're recording stuff. So, we have the Ferris wheel, and this is B. Okay, so B is going around at 0.4, so omega equals 0.4 radians per second. Okay, I already kind of implied this before. I'm going to say it again just to really annoy you guys. Do good free body diagrams. You need to have good free body diagrams. A free body diagram can make or break a question, okay? It literally just makes it so much easier for you to digest. And if you have a bad one, you end up needing to redraw it and you just waste time. So that is what I'm going to do, draw B as, okay? 10. I'm going to move this because I want to show us the velocity of B. That now looks a little bit weird. Okay, so what's the velocity of B? Well, B is going to just be moving tangentially at any given time, or like the velocity vector would be tangential. Okay, and VB is that. Okay, but we can decompose it. We've done this a lot today. Decompose it into our horizontal components. And this is also 30 degrees, which you can just achieve through simple parallel lines, because that's 30 degrees. And then because that's 30 degrees, this is 60 degrees, because that's a right angle. And then because that's 60 degrees, this is 30 degrees, okay? Yeah, so that's that. Okay, so I'm pretty sure that's all the information we need. I guess, sorry, we should actually add the car as well. Look at my brilliant car. And we know the velocity of the car is 5 meters per second. And we also know the velocity b. Well, we don't know the velocity b, but we do know the angular velocity. And how do we get from angular velocity to linear velocity? Well, v equals r omega. Okay? So we know that the velocity of b, hence, will be 10 times 0.4, which equals, I don't know why I didn't just, why I need to look at, obviously 4, sorry. Mental maths is not my strong suit, I guess. Yeah, so 4 meters per second. So we know that the velocity of b is 4 meters per second, okay, in that direction. So it is moving 4 meters per second in this direction, but we want to decompose that into our x and y components, okay? So the polar coordinates, I suppose, would be, well, the x-wise, it's going left, okay, and it's sine. So it's minus 4 sine 30 degrees, I, okay, this is we're now bringing in our polar coordinates, is now I and j, okay, plus 4 cos 30 degrees j, okay. iPad is literally on fire right now. It's like crazy, because if I'm charging it, and it's also like 30 degrees right now, I think. Oh, it's only 21. Okay, I don't know why it's so hot in my bedroom. Yeah, okay, that's weird. So that's VB, and then VA is just 5I, okay, because it's actually going to the right. Okay, so now we're actually like already pretty much done, okay? So VAB is 5I minus minus 4 sine 30I plus 4 cos 30j. So let's group that together. We end up with the 5 minus, plus, because the minus is cancelled out, sine 30I minus 4 cos 30j. The minuses don't really matter because the question has asked us for the magnitude. It doesn't matter about the sign. So the Vx component is, well, he did 5, well, sine 30 is half, so it ends up being 5 plus 2. That's 7 meters per second. And minus 4 cos 30 is, and I'm sorry, I've actually put this wrong in the answers. I will probably try, if I remember, I will correct this. It doesn't lead to a terribly incorrect answer, and that's why I didn't notice. You end up with minus 3.464 meters per second. So VAB, the magnitude, is just the square root of 7 squared plus minus 3.464 squared. And you should get 7.81 meters per second. And the answers, I've written 7.28, which as you can tell is not very different, which is why I didn't notice that it was wrong. So it should be 7.81 meters per second, okay? This one's pretty straightforward. I would actually say in terms of dynamics, Kellerman is kind of being nice to you here, but it kind of ends there because the next few are not as easy. Continuing on, we are making good progress. It's 6:40. I think I can finish this one and the next one, and then we're going to have to probably pause. All right, so part B is, I'll scroll back up while I take a sip. Determine the magnitude of the acceleration of the car A relative to B. Okay, so this one is a little bit harder and it requires us to remember some things about angular acceleration, okay? Namely the fact that the acceleration of an object going in circular motion will be its tangential acceleration plus its normal acceleration. You need to remember that, okay? So, let's do it. I actually just do it on the same page, probably easier. So, I'm going to duplicate this diagram. One great thing about iPad exam is you can just copy paste, but also I think he knew that, which is probably why he gave us so many new like diagram questions. So we're going to have acceleration in that direction, and okay, we're also going to have acceleration here, and that should be, I think it was just 2. Meters per second squared. Okay, so we have acceleration in that direction. Again, it's 30 degrees, but then we also, so that's just the tangential acceleration. So this time we actually have 2 components. We also have a normal acceleration pointing inwards. Okay, now, fun fact about tangential acceleration. If the angular velocity, or the velocity in general, is constant, and it is in this case, the tangential acceleration is 0 because it's not accelerating in that direction. Okay, think about it. The tangential acceleration is along the same plane as the velocity. The velocity is constant, so the tangential acceleration must also be 0. Okay, so this is part B. The tangential acceleration of the chair is 0. Okay, constant velocity. Okay, now time for us to recall a very important equation. So we got to find now the normal acceleration of the chair. This will equal, you could either say it is v squared over r, or you could say omega squared r. Okay, so it'll be, because that's just like, that's the formula for normal acceleration, it's just omega squared r or v squared over r. V squared was 10, was it? Hang on, was it 10? Sorry, I'm blanking. Sorry, v squared was it 4? 5. No, it was 4. Yeah, it was 4. Yeah, okay. So v squared was 4. So 4 squared over r, sorry, v was 4, v squared is 16, and then r was just 10. And that should give you 1.6 meters per second squared. Okay, so we now know that the normal acceleration is 1.6. Let's decompose it as usual. Both components are going to be negative. So that should equal minus 1.6 cos 30i minus 1.6 sine 30j. Okay? Yeah, that's it. So, what is the acceleration of the chair? Well, as I was just telling you, it'll be the acceleration of, it'll be the tangential plus the normal, which is 1.6 minus 1.6, sorry, it's 0 minus 1.6 cos 30i minus 1.6 sine 30j. Okay. All right, and what about the car? Well, the car is the easier one because the car is only accelerating on one plane. It's just accelerating to the right, so it's just 2i. Okay. So remember, it's the exact relative acceleration. It'll be the same as relative velocity. So the acceleration of A relative to B, which is the question, it'll just be the acceleration of A, and A is the chair. A is the car. Okay. Double check when you're going through the question. Make sure that the chair and the car, you have them correct. In this case, the car is A. Okay. Minus the chair, so you end up with plus 1.6 cos 30i plus 1.6 sine 30j. All right. Okay. So you end up with an x component. Oh, I have oh no, that's a different. Yeah, sorry, I'm thinking of the next question. There's a step that I need to remember, but that's not for this question. Okay, so you end up with an x component of 2 plus 1.6 cos 30, which should be 3.39, and a y component of 1.6 sine 30. If you've memorized your trig numbers, you know the exact values, you know that's 0.8. Okay, and the magnitude should be just the square root of 3.39 squared plus 0.8 squared, and that should bring us to 3.48 meters per second squared. Boom. Okay, so that is the answer to this question. Hope that makes sense. Again, I actually think this is surprisingly straightforward for a Kellerman question, but you know, you can never be too careful of that man. He can give you some really tough stuff, so be prepared for anything, guys. Okay, so I'll do one more question, then I'm gonna have to tutor my student, and then we'll get back to it after dinner. Okay, so we're gonna do this, but I should probably stop the recording just to make sure everything is going well. One moment. All right, so question 6 is, how do I say this? It's actually like, okay, so it's worth 4 marks, which is pretty insane. I don't think any other question in this paper is worth 4 marks. But it's actually not that bad. I actually got it in the test, and I'm pretty sure I got it right. Yeah, there was actually a mistake I did make, but that was at the very end, and I will tell you what it is when I get to it. But it's actually, this is a relatively doable question, but it is daunting because it's 4 marks, and I do despite it being doable, I do think it is worth 4 marks. So definitely give this a try on your own before you watch this. Actually, you should be doing that for the whole paper, to be honest. That's the best way to practice. So, particle energy and momentum. Particle A and particle B strike each other as shown in the diagram below. The coefficient of restitution between the particles are equal to E. Determine the magnitude of the velocity of both the particles A and B just after collision. Okay, well, this is a coefficient of restitution question, which is probably obvious from the fact that it says that in the question. And what is the coefficient of restitution? Well, it's important to actually know what the formula is, okay? And kind of like get ready for this, okay? The coefficient of restitution, well, first of all, what is the question asking? It's asking us to find the velocities of A and B after the collision. Well, E is the coefficient of restitution, and that is V2 dash minus V1 dash over V1 minus V2. That is the coefficient of restitution formula, and that is what we're trying to figure out. Okay, we have V1 and V2, okay? I assume these are meant to say millimeters per second. I don't know why they don't. We have those two, but we don't have V-2 and V-1. We have two unknowns, only one equation, okay? The rule of simultaneous equations, you need to have as many equations as unknowns, okay? So we obviously need some sort of other equation or some other way to find V-2 or V-1. All right, but let's just begin. And the way we're going to begin is with a good free body diagram. Yeah, to save myself time, I think I've done so many free body diagrams this session. I'm going to just copy the one I did in my exam, and I'll just talk you through how I drew it. Oh no, I did a new one today. I'll show you that one instead. Be this one, I think. I think the one I did in the crash course itself was pretty good. So I now have 3 copies of the same paper. The one I did on the day itself in 2023, and then the one I did today for the crash course, and then the one I'm doing right now for this recording. Okay, so this is the collision. I've drawn it out as a free body diagram. And I've also done all the angles and the trigonometry, and I believe you're all capable of figuring it out yourself. But if you're wondering, we figured out 22.6 because we didn't actually find that side length, but we know this is 50 because the diameter of the smaller particle is 50. And then we know this is 130 because this is 80 and this is 50. And you just use tan inverse to find 22.6. Okay, and then you know every single particle. This particle is hitting at an angle of 22.6. This angle is hitting at a angle of 22.6. Okay, and then you can resolve all the velocities. Okay, so that is the first step. Okay, let's resolve the velocity of particle 1. So particle 1 is, okay, so it's going up and to the right. So it's 3 sine 22.6 cos 22.6 I plus 3, because it's going up, sine 22.6j. V2, on the other hand, is actually the exact opposite. They're going to both be negatives, but it's going down and to the left. So it'll be minus 2 cos 22.6i minus 2 sine 22.6j. Okay, that is our initial velocities. We've now gotten the initial velocities. Okay, but it's not quite time to plug it into E yet. I mean, you could, but I've chosen to do it differently, which is I've chosen to bring in the conservation of linear momentum equation. M1M2 plus M1V1 plus M2V2 equals M1V1 dash plus M2V2 dash. Okay, so the velocity, so the momentum before the collision has to be the same after the collision. We know that we're obviously going to lose some energy, but overall, the momentum needs to stay the same. Okay, otherwise, like the momentum needs to go somewhere. In reality, obviously, you have heat loss and all of that stuff, but you know, it all needs to go somewhere. Basically, that's kind of what this equation is trying to say. Yeah, I'm pretty sure that's right. And that accounts for like masses and stuff. Okay, so basically, if we sub everything in, so mass is 5 times 3 cos 22.6i plus 3 sine 22.6j plus 6 minus 2 cos 22.6i minus 2 sine 22.6j equals 5 v1 dash plus 6 v2 dash. That is where we're at right now. Okay, and then if we simplify the whole left-hand side, it's obviously a huge mess. 5v1 dash plus 6v2 dash, you end up with 2.74i plus 1.16j. Okay, so we've now got our first kind of bit, I guess. All right. So then, what's E? Well, E, I told you before, it is v2 dash minus v1 dash over v1 minus v2. All right. We were told what E was. We were told E is 0.5. Sub in, so for V, sub in this stuff, okay? And you would end up, if I was just to simplify it for you guys to save us a bit of time, you end up with 4.62i plus 1.92j, okay? So, expand, you end up with, so multiply out, 2.31i plus 0.96j equals v2 dash minus v1 dash. I'm going to multiply that all by 5, and you'll see why in a minute. Let's multiply it by 5. 11.55i plus 4.8j equals 5 v1 dash, so we do v2 dash, minus 5 v1 dash. Okay, why have I done that? Well, that's because we're now going to bring in this equation. Okay, we're going to now bring in that one, 2.74i plus 1.16j equals 6v2 dash plus 5v1 dash. Okay, classic elimination method of simultaneous equations. I'm just going to now add those two together and boom, we now get rid of the v1s. Okay, so 14.29i plus 5.96j equals 11 v2 dash, and then you end up with v2 dash equals 1.3i plus 0.54j. Okay, and if you were to sub back in, I assume you all know how to just like sub that back into like any equation you want. You can sub it into this one even. You should end up with v1 is minus 1.01i minus 0.42j. Okay, what is the magnitude? Well, magnitude of v2 dash, because that's what the question asks. 1.3 squared plus 0.54 squared, and you end up with 1.41 meters per second. v1 dash is similar thing. .09 meters per second. Oop. Okay. And it's just asked for magnitude and asked for direction or anything. So that's it. That is how you find the magnitude of particles 1 and 2. So that one's actually like pretty straightforward once you know how to do it, but it is certainly a trek. It is certainly a huge trek, and it's probably a good example of civil in general. Well, a lot of the questions are not technically hard, but it's just like a trek to solve them, and you will experience this when you get to, I think steels in particular ends up being a lot like this. That you won't be doing that for another year and a bit, I reckon. Unless you're crazy and you try to do it in term 1. I don't even think you'd be allowed to do it in term 1, because you need to do solids first. Yeah, so that's that. I'm gonna take a break. I need to go tutor my student, and then I will have dinner, and then I will come back to you guys. So bye-bye. Alright, hello everyone. It's now 9:30. It's been 2.5 hours since I was last talking to you all, but I guess in the magic of editing it's probably only been like 1 second. So let's do the next question. This is the last one I'm going to do. Question 8. So question 8 and 3, I'm going to leave those. To question 3, I think the answers that I've got, check the description. I think the answers are pretty clear on that, and you can use that. Question 8, I'm just simply not 100% confident my answer is correct. I think it probably is. You can look at my working out, but and I think my working out makes sense. So have a look at it, but I'm just not like completely confident with it. So I'm gonna just skip that one. It's a pretty hard one, that one. But I do have the solution there. So if you do want to check, do just look at my solution. It's online. But I just say that with the caveat that I'm not 100% confident with it. But I'm like 70% confident, I guess. Okay, so the mass M2 is suspended through a rope on the compound pulley, having a mass M wheel and a radius of gyration K about an axis passing through O. As the mass M2 falls, it pulls the mass M1, causing it to slide along the smooth horizontal surface on which it rests. The rest of the question got cut off, so I'm just going to insert it. That's the rest of the question. Okay, so determine the magnitude of the angular acceleration of the compound pulley. That's 2 marks. And then determine the magnitude of the horizontal and vertical components. Part B is really straightforward, and I'm not sure why it's 2 marks. Part A is not as straightforward, so it makes sense that's 2 marks. Okay, so we've done so many FBDs today that I'm just going to copy in this FBD that I did, like in today's workshop. So this is the FBD that kind of summarizes the diagram, okay? So what we basically have, and remember, in this case, we have F equals MA. So that's the formula we're using. We're using some of the forces is going to be F is MA. Okay, so we're now bringing acceleration into this, okay? We're now bringing that law, Newton's law into it. So, in this case, so this is the mass that's pulling it down, okay? It weighs 40 kilos. So of course, gravity, when you'll remember from Phys 1A, you got to consider gravity if it's like down, I guess. So 40 times 9.81, but then you also have to need to consider MA. So MA is acceleration, so 40A. So what you end up with is 40A plus 392, okay? So that's this force. And then going this way is 25A, okay? Which I don't really, there's not really anything new to that. It's just that it's 25 and it's acceleration, okay? And let me just check everything. I think that is pretty much it. Yeah. So I'm pretty sure because acceleration, because this is going to be going this way, and it's just, so in the workshop I was a bit confused, but I think this is the explanation. Because this is accelerating to the right, both of these are moving to the right, okay? So in part A, they're both moving to the right, but then in part B, as we'll see, is a bit different to that. So we're going to use this law. So M is I alpha, okay? Which is just, it's summation of moments, okay? So I equals mk squared. You need to remember that. It's pretty straightforward. We are told the mass of the wheel is 50. And k is 0.11. So that just ends up with 0.605 kilogram meters. Okay? So T1. Okay, so we're going to say that's T1. Or we could even say F1 might be a bit neater because it's not technically T. It's not tension. It's actually force. So F1 is 25A, and then F2 is 40A plus 392. But remember, this equation is in alpha. It's on terms of A, so that's important. So linear acceleration equals R alpha. All right, kind of like the angular acceleration and all that. Sorry, linear velocity. I meant. So F1 is actually 25 times the radius, okay, which is 0.25 times alpha. Oh, no, it'd be 6.25. Okay, and then F2, similar thing, if you were to do it, it would be R, which is 0.5, 40 times 0.5 times alpha plus 392, which is literally just 20 alpha plus 392. Okay, so now we've gotten all our equations like nice and set up. So let's sub it into this equation now. Okay, so Sum of the moments, okay, so 25A, okay, but it'll be negative, right? Because it's going clockwise. So, because we're doing the sum of the measurements about this point here, okay? Minus 25A, and you need to multiply it by the lever arm, which is 0.25. Sorry, minus 6.25 alpha. So we need to actually sub it in. Minus 6.25 alpha times 0.25. This is also going to induce a clockwise moment, so it's negative as well. And we've got to multiply by the lever arm, which is 0.5. And that should be equal to 0.605 alpha. Okay, so if you simplify all of that out, you end up with minus 1.5625 alpha minus 10 alpha minus 196 equals 0.605 alpha. And that leaves you with alpha is minus 16.11 radians per second squared, which means it's accelerating clockwise. Okay, so 16.11 radians per second squared. Okay, now again, as we did before, you want to do a sense check. Okay, does it make sense that this would be accelerating clockwise? Well, this is bringing it down, which is bringing this that way. So obviously that's going to be making it go round and round and round and round and round and round. It's definitely clockwise, right? So that makes sense. So, and you should actually add that in clockwise. Okay. So that is part A, and then part B is actually deceptively simple, which is literally tension is so the tension. We're now going to be talking about tension. So T2 is basically the same as F2. Okay, so T2, but in this case T1 is actually pointing left. Okay, equals 6.25 alpha. Okay, and T2 is actually, if we were to simplify it now that we have all the information, we would end up with, so if we were to simplify both of these, we end up with T1 is 100.7 newtons, and we end up with T2 is 69.9 newtons. So, part B, well, straight away, what we're trying to find for part B, I should actually tell you. So this point is O, okay? So what we're trying to find is OY and OX, okay? That's straightforward. So, summation of fx is OX, sorry, it should be 0 because it's an equilibrium. So OX is positive, minus 100.7 because of T1, sorry, because the tension is going to be pointing left. That equals 0. So OX is 100.7 kilonewtons. Sorry, it might be newtons. Sorry, I think it's newtons. Okay, and then Fy is pretty much the same thing. 69.9, sorry, it's 0. So, OY minus 69.9 equals 0. But, hang on, that's actually not it, because there's also the mass of the wheel itself, which is 50 times 9.8, which ends up being, I didn't actually write it down, let me check, 50 times 9.8, 490. Okay? Oh, sorry, I'm getting a call, 1 moment. Alright, so OY minus 69.9, and then it's minus 490 actually. So this is minus 490 equals 0. So what you end up with is OY equals 560.4 newtons, and that's the whole of part B. Yeah, so that's where I'm going to leave it. I've done an answer for question 8, so feel free to have a look at that, and if it hopefully it makes sense. Where is it? I don't even know where it's gone. Oh, it's probably here actually. So I got a solution to part 8, and I think it's probably correct. Yeah, so just do have a look at that. I put that question to ChatGPT and it got a very similar answer. It wasn't exactly the same, but it was like it got like 31.8 instead of 30.4 or something like that. Yeah, no. So I guess in terms of general advice for ENGG1300, I think just revise everything. Probably spend a bit more time on dynamics because I feel like I personally think it's harder. I think there's also a reason why it comes second in the course and not first. Granted, a lot of dynamics relies on statics knowledge, like equilibrium and stuff. And definitely revise the last few weeks the most, because having run this crash course, that was the stuff I struggled with the most, and I think I already said that. whereas the static stuff was much easier. And I don't know if that's because I did 1300 2 years ago, or if it's because the dynamic stuff is actually harder. I think it's because the dynamic stuff is actually harder. Yeah. Anyway, I hope this session was helpful. And let me know any feedback in the comments, I guess. Thank you.